Right now, PSR J0952-0607 is still spinning 707 times every single second, and NASA has no way to stop it. The smartest physicists on Earth have measured what's inside it. They've run the numbers. They've checked them twice. And what they found breaks one of the most fundamental rules in astrophysics. But here's what nobody is telling you. PSR J952607 is a neutron star. And if you think you know what that means, you don't. Not yet. When a massive star, one at least 8 times the mass of our Sun, exhausts its fuel and collapses, the explosion is called a supernova. It is powerful enough to briefly outshine an entire galaxy. What gets left behind, the crushed core, is a neutron star, a ball of matter so dense that a teaspoon of it weighs 1 billion tons. Not metaphorically, literally. 1 teaspoon, 1 billion tons. This particular neutron star sits about 3,000 light-years from Earth in the constellation Sextans. It was quietly spinning out there, undetected, until the world's largest radio telescope locked onto its signal. Scientists classified it as a pulsar, a rapidly rotating neutron star that sweeps beams of radio waves across space like a lighthouse that never rests. They were not ready for what they measured next. Every neutron star has a weight limit. Physics sets it. It is called the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can hold before gravity wins completely and crushes it into a black hole. For decades, the calculation landed at roughly 2 times the mass of our Sun. Some models pushed it toward 2.5. A few theorists argued even higher, but no one had found a neutron star massive enough to seriously test the ceiling. PSR J952607 came in at 2.35 solar masses. That number stopped people cold, because 2.35 solar masses means this neutron star is pressing hard against the edge of what should physically exist. The matter inside it is under pressures no laboratory on Earth has ever come close to recreating. Pressures so extreme that the laws of physics we trust every day, the equations written in every textbook, begin to fail. And that's not even the part that worries them. The obvious explanation is that it consumed its companion star. Neutron stars in binary systems can pull material from their partner over millions of years and slowly build mass. That process is called accretion. Scientists understand accretion. They have well-tested equations for it, but accretion has limits too. The companion this pulsar is orbiting is barely there. A stripped, exhausted remnant. A thin shell of what it used to be. Scientists call this arrangement a black widow pulsar, a neutron star that has fed on its partner until almost nothing remains. What's left orbits PSR J952607 every 6.4 hours. The mass gained through accretion doesn't fully account for the reading they got. Something about this object's interior is resisting forces that should have already crushed it out of existence. Here is the part they're afraid to say out loud. Inside a neutron star this massive, the pressure at the core is so extreme that individual protons and neutrons may no longer exist as we know them. The boundaries between subatomic particles could dissolve entirely. What you get instead is something physicists call quark matter, a dense, exotic soup of the fundamental building blocks of reality, freed from the particles that normally contain them. Quark matter has never been observed on Earth. We cannot make it. We cannot study it directly. We can only infer its existence from the outside, from the mass, the spin, the measured behavior of objects like PSR J952607. And here is the strange part. It shouldn't be possible at all. The standard model of particle physics, the most tested, most rigorously verified rulebook in all of science, does not fully account for what happens when matter is compressed this far. The equations disagree with each other. Different theoretical models produce incompatible answers, and the real universe, spinning out there 707 times per second, does not care which model we prefer. Researchers published their findings in the Astrophysical Journal Letters and flagged the mass reading as extraordinary. They used words like constraints and challenges. Those are scientist words for, we don't have an explanation that fully satisfies us. This thing is too heavy. And we don't know why it isn't already a black hole. What does that mean for us? It means the matter at the center of PSR J0952-0607 is the densest form of matter currently known to exist anywhere in the observable universe, and we have no confirmed working theory that describes it. Every textbook on particle physics, every simulation of stellar collapse, every model of nuclear matter has to be recalibrated around what this object is doing right now, in real time, 3,000 light-years away. The reading from PSR J0952-0607 doesn't just challenge one equation. It challenges the foundation those equations are built on. Think about what that means. The physics behind particle accelerators, the physics inside nuclear reactors, the physics that underpins the most powerful technologies humans have ever created. All of it traces back to a model of matter that this neutron star is silently, continuously breaking. It has been doing it for millions of years. It will keep doing it long after every single person alive today is gone. And the question no one can answer: if PSR J952-0607 is already this far beyond what our models predicted, how many more are spinning out there right now, in the dark, waiting to be found? Tell me in the comments what you think is actually hiding inside it.